All right, let's dive into something a little unsettling today. We're going to be looking at the security of those massive data sets. You know, the ones used to train all those cutting-edge AI models.
Yeah, these data sets are getting huge.
Yeah.
And that's great for model performance.
Right.
But the problem is they're basically impossible to curate manually.
Right.
So that opens the door for some pretty clever attacks.
Yeah, and we've got a paper here that really dives into this.
Yep.
Carlini, idle, 23 EVA 2.10149, poisoning web-scale training data sets is practical. And that's what we're going to be looking at.
Yeah, and this paper doesn't just like theorize about these attacks.
Oh, yeah.
It really gets into like how practical they are.
Yeah.
Like real world attack vectors.
And it shows how feasible it would be to actually poison these data sets. And honestly, how cheap it would be.
Yeah.
Kind of scary.
Yeah, they focus on two main types of attacks.
Yeah.
Split view poisoning and front-running poisoning. And they both kind of leverage these inherent vulnerabilities in how these data sets are built and how we use them.
So let's start with split view poisoning.
Right.
This one plays on the fact that a lot of these data sets are distributed.
Mm-hmm.
They essentially give you this giant list of URLs and labels.
Right.
But you got to go and download all the data yourself.
Yeah.
What could possibly go wrong there?
Well, they found that most of these distributed data sets, they don't have any kind of integrity checks. They don't verify that the data that you download from a given URL is actually like what it's supposed to be,
Okay.
what the maintainers originally indexed. So an attacker could like buy up a bunch of expired domains that are listed in the data set,
Okay.
replace the content with poison data,
Okay.
and there you go.
So how often are domains in these data sets actually expiring, though?
Yeah, that's a good question.
Is that really a realistic attack vector?
Yeah, it's more often than you think. If you look at Table 1 in the paper,
Yeah.
it's kind of eye-opening. They looked at a bunch of popular data sets,
Yeah.
and like a significant percentage of the domains in those data sets had actually expired. In some cases, it was as high as like 20%.
Wow, that's a huge attack surface.
Yeah.
But okay, so let's say like you're an attacker.
Yeah.
How expensive would it be to buy up enough domains to actually like have a real impact?
Yeah. It's surprisingly cheap.
Okay.
Like the paper shows you can poison like 0.01% of LAI on 400M for just $60.
$60.
Yeah.
That's insane. But I mean, how many people are actually downloading these huge data sets in their entirety?
Yeah, that's a good question.
What do you have to kind of target, like a specific subset that someone's using?
Yeah. The researchers actually, they measured this.
Oh, wow.
They monitored traffic to expired domains that they had bought.
Okay.
And it turns out that even the less popular data sets, you know, they get a few full downloads each month.
Mm-hmm.
And then, of course, you've got, you know, tons of smaller curated data sets that are derived from these bigger ones.
Oh, yeah.
So the poison could, like, propagate downstream.
So you're not just poisoning that one, you might be poisoning a whole bunch.
Yeah.
Okay, so is this happening already?
Yeah. Did they find, like, any evidence of this in the wild?
Yeah.
So they did find evidence of domain squatting,
Okay.
but no clear signs of, like, malicious intent,
Okay.
at least not yet.
Not yet. Okay, but let's move beyond the potential.
Mm-hmm.
Did they actually show how effective this could be?
Yeah, so they showed that with a budget of just $1,000.
Okay.
They could poison LA on 400M enough to manipulate a model's object classification.
Oh, wow.
Like, they could make a model falsely flag certain images as NSFW.
So even without changing the labels themselves,
Yeah.
just by swapping out the images.
Yeah, just swapping the images.
That's crazy. That's really disturbing.
It's like a supply chain attack,
Yeah.
but for data.
All right, so we've talked about split view poisoning. Let's move on to the second one. This is front-running poisoning, and this one even more insidious, I think.
Yeah.
This one targets data sets that are built from website snapshots, particularly Wikipedia.
Yeah.
And the key here is how deterministic Wikipedia's snapshotting process is.
Right.
You can actually predict when a specific Wikipedia article will be scraped for a data set with pretty high accuracy.
Yeah, that's crazy.
How is that even possible? How do you predict something like that?
So it's all about understanding like the mechanics of how these snapshots are actually taken. Wikipedia articles, they're processed in this predictable sequence.
Oh, okay.
Almost like this sawtooth pattern. And figure 3 in the paper shows you what that looks like.
So an attacker could kind of look at this pattern, figure out when a specific article is going to be scraped,
Right.
and then just slip in a malicious edit. right before the snapshot happens.
Exactly. And even if that edit gets reverted quickly on the live Wikipedia page, the poison version is already like beaked into that data set snapshot.
Oh, wow. That's really clever.
Yeah.
How accurate are these predictions in practice, though? Like, could you really reliably time your edit to be within that snapshot window?
Yeah, so they dug into historical edit timestamps,
Yeah.
and they found that they could often predict the snapshot times within a 30-minute window.
30 minutes. That's pretty good.
Yeah.
But I mean, how long does it usually take for malicious edits to get reverted on Wikipedia?
Right, because that's the attacker's dilemma.
Right.
They have to time it late enough that it doesn't get reverted before the snapshot.
Right.
But early enough that they don't, miss that window.
Yeah, it's a tough one.
So they looked at 18 months of edit data,
Okay.
focused on reversions that were based on specific keywords.
Okay.
And the average reversion time was about 30 minutes. But it varied a lot, Figure 6 shows you the distribution of these reversion times.
So it's a race against time. They got to really understand that distribution
Yeah, exactly.
to really maximize their chances of success.
And so by combining their prediction accuracy and their knowledge of these reversion times, they estimated that they could poison 6.5% of Wikipedia documents using this method.
6.5%. That's a lot.
Yeah.
I mean, they do say that in the real world, that number might be lower.
Right.
But still, that's a big number.
Yeah, it's significant. It really shows how these temporary edits can have these lasting consequences when it comes to training data.
Yeah.
And the paper kind of hints that, similar vulnerabilities might exist for other web scale data sets too.
Like Common Crawl and things like that.
Yeah.
Okay, so this is all pretty concerning.
Mm-hmm.
When we come back, let's talk about some of the defenses that they propose.
Yeah.
And we can see, if we can safeguard these data sets against these attacks.
All right, so let's dive into some potential defenses against these attacks.
Okay.
Starting with split view poisoning and those expired domains.
Right.
Remember, the core issue there is we're not verifying the data when we download it.
Right. Right.
It's like assuming a library book always has the same content,
Yeah.
even if someone else borrowed it before you.
Yeah. So how do we fix that?
Well, we need some kind of digital fingerprint, right?
Okay.
To make sure that the data hasn't been tampered with.
So like a checksum or something.
Exactly. The paper suggests using cryptographic hashes.
Okay.
So the dataset maintainers would calculate these hashes for the original data
Right.
and include them in the index.
Okay.
And then when you download the data, your tool would compare the hash of what you downloaded to the original.
Okay.
And if they don't match,
Big red flag.
red flag.
Makes sense.
Sounds pretty straightforward, right?
Yeah.
But there are some challenges.
Okay.
This assumes that the content at a URL never changes for legitimate reasons.
Yeah.
But websites get updated all the time.
Course.
Images get reformatted.
Right. Yeah.
These are all perfectly normal changes.
Yeah.
But they could trigger a hash mismatch
Oh, I see.
and lead to discarding good data.
So you might be throwing out the baby with the bathwater.
Exactly.
How do we balance that? Like the need for security with the fact that web content is dynamic,
Right.
constantly changing.
It's a tough question.
Yeah.
The researchers actually looked at this.
Okay.
They found that even for a relatively old data set like conceptual captions,
Yeah.
over half the images had changed in some way
Really?
since the initial release.
Wow.
Not maliciously, just resized, watermarks added, that sort of thing.
Okay.
The paper briefly mentions perceptual hashing as an alternative.
Okay. What's that?
So instead of doing like a bit-for-bit comparison,
Right.
it looks for similarities in the content itself.
Oh, interesting.
So minor changes might not trigger a mismatch,
So that could solve the problem.
potentially. But it's not a perfect solution.
Right.
Perceptual hashing is more flexible, but it's also less secure.
Okay.
A really clever attacker might be able to craft poisoned data
Yeah.
that's similar enough to the original to fool the hash.
Oh, that's tricky.
It's an ongoing area of research. There's no silver bullet yet.
Okay, so integrity checks are a good step,
Mm-hmm.
but they're not foolproof.
Right.
What about front-running poisoning? How do we disrupt those predictable snapshot timings?
So for front running, the key is randomness.
Good.
The paper suggests two main approaches.
All right.
First, randomize the order in which Wikipedia articles are snapshotted.
Right.
Instead of going sequentially by article ID,
Right.
just shuffle things up.
Make it a lot harder for the attacker to predict when a specific article is going to be scraped.
Exactly.
Okay, what's the second approach?
Delayed snapshotting.
Okay.
So instead of grabbing the live version of every article,
Yeah.
Wikipedia could take a copy
Okay.
and then wait say, a day or two
Right.
before actually finalizing the snapshot.
Oh, I see.
So during that waiting period,
Okay.
any malicious edits would likely be caught and reverted.
Yeah, by the regular Wikipedia editors.
Exactly.
And since the snapshot is based on that slightly older copy,
Right.
the poisoned data never makes it in.
Right. It's a clever idea.
Yeah, that's clever.
But of course, there's a trade-off there.
Yeah, I mean, how fresh does the data need to be?
Right. You're introducing a delay.
Is worth the security.
Exactly. And it might not completely eliminate the risk.
Right.
An attacker could still target less popular articles
Oh, yeah.
or Wikipedias in other languages.
Where the moderation might be slower.
Exactly.
Yeah, that makes sense.
So vigilance is still key.
Okay.
We can't just rely on technical solutions alone.
Right.
This brings up a bigger point about the trust we place in these data sets.
Yeah, there's a lot of implicit trust right now.
Exactly.
We trust the maintainers, the curators,
The downloader.
the downloads, everyone involved.
Yeah.
But this research shows that trust can be misplaced.
That's right, and that's why the paper calls for more transparency
Okay.
in the entire ecosystem.
Look, what kinds of things?
Things like publicly logging the URLs and hashes used in a data set
Okay.
so that anyone can verify the integrity of their data.
Oh, okay, so independent verification.
Exactly.
Okay.
Or being more transparent about the snapshotting process itself.
Okay.
So instead of this kind of blind trust,
Right.
we need systems that allow for verification and accountability.
So we need to know where the data came from,
Yeah.
what happened to it along the way,
Right.
who's touched it.
And especially with this increasing reliance on these massive uncurated data sets,
Right.
what kind of trust mechanisms are really robust enough
Yeah, that's
for these kinds of challenges?
that's where it gets interesting.
That's where it gets really interesting.
Yeah.
This paper is just scratching the surface.
Right.
We need to explore more robust solutions, maybe even leveraging, distributed ledger technologies or cryptographic signatures to track the provenance and integrity of the data.
So we need to build in safeguards
Yeah.
into the very DNA of AI development.
Exactly.
Consider security from the get-go.
Right. It can't be an afterthought.
All right, well, I think that's a good place to stop for now.
Okay.
When we come back, let's wrap up by looking at kind of the broader implications of all this
Sounds good.
and what it might mean for the future of AI. All right, so we spent the last two parts of this deep dive really digging into Carlini AD's Pearce paper on poisoning web-scale data sets and some pretty thought-provoking stuff.
Yeah, for sure.
We've seen how these attacks work. We've talked about some potential defenses.
Right.
But I think now it's time to kind of zoom out a bit.
Yeah.
What are the bigger implications of this research? Like, what does it mean for the future of AI, especially as our models rely more and more on these, giant data sets that are out there?
That's the million-dollar question, right? Like, if we can't trust the data that's going into these AI systems,
Yeah.
what does that say about how reliable or safe those systems actually are?
It's a little unsettling, to be honest.
Yeah.
I mean, imagine you've got like a large language model that's been trained on a poisoned version of Wikipedia.
Right.
Like, it could be generating text that's biased,
Totally.
factually incorrect, even spreading misinformation.
Yeah.
And we might not even realize it.
Yeah, it's scary.
And it goes way beyond language models, right?
Oh, absolutely.
Think about like self-driving cars
Yeah.
that are trained on these data sets of street scenes.
Right.
What if someone poisoned those data sets so that the car misinterprets a traffic sign?
Exactly.
That could lead to some really dangerous decisions.
Yeah.
And the scary part is like, how do you even detect this kind of poisoning?
Right.
We're not talking about like blatant malware here.
Right. It's subtle.
It's these subtle manipulations that could easily just fly under the radar.
It really highlights the need for a much more holistic approach to AI security.
Right.
We can't just focus on the algorithms themselves.
Yeah.
We need to think about the whole pipeline.
So from data collection.
Yeah, all the way to deployment,
Right.
with security and integrity as like core principles at every step.
So where do we go from here?
That's a great question.
Like, what are the most important research questions, given all this?
Well, for one, we need much better ways to detect these poisoning attacks.
Okay.
Traditional cybersecurity tools, they might not be enough.
Right.
We might need techniques that are specifically designed to analyze these massive data sets
Yeah.
and look for those subtle statistical fingerprints of poisoned data.
So like a digital detective
Yeah, exactly.
sifting through mountains of data looking for those telltale signs. What else? What else do we need?
We need to develop much more robust trust mechanisms.
Okay.
Transparency is a good start,
Yeah.
but it's not enough on its own.
Right.
We need ways to actually verify the provenance and integrity of the data.
Okay.
Maybe using things like distributed ledger technologies or cryptographic signatures.
So you could track the history of a piece of data.
Yeah.
See who created it,
Mm-hmm.
how it's been modified,
Right. Has it been validated?
whether it's been validated.
By trusted sources.
Wow.
That kind of transparency, that could be a real game changer.
That would change everything.
Yeah.
So moving from just like blind trust
Mm-hmm.
to this system where we've got like verifiable accountability for the data.
Absolutely, especially as we become more reliant on these huge data sets.
Right, right.
And, maybe even more importantly, we need to foster this culture of responsible AI development.
Okay.
Security can't be something we think about later.
Yeah.
It needs to be baked into the DNA of AI from the very beginning.
So building those safeguards in from day one,
Exactly.
making security and integrity just as fundamental as the algorithms themselves.
That's right. And it's not just on the researchers and developers either.
Right. Who else needs to be involved?
Policymakers.
Okay. Regulators.
They need to be part of this.
They need to be part of the conversation.
Okay.
We may need new guidelines, new standards to make sure that these AI systems are secure and trustworthy.
Especially in areas like healthcare and finance.
Yeah.
Where the stakes are really high.
High stakes.
So this isn't just a technical challenge then.
Right.
It's a societal one.
It is.
And it needs kind of a multi-pronged approach, right?
Mm-hmm.
We need the technical experts.
Yeah.
We need the people who are responsible for governance.
Absolutely.
And oversight.
We need everyone.
It's a big challenge.
It is, and it's only going to get more urgent as AI becomes more integrated into our lives.
Yeah, I think that's a really good point.
This research is a wake-up call.
Mm-hmm.
It's a reminder that the security of AI is completely tied to the security of the data that it's built on.
Well, I think that's a good place to wrap up our deep dive.
Okay. You've explored the vulnerabilities,
Yeah.
the potential defenses, and really some of the broader implications of these poisoning attacks.
And hopefully this has equipped you, the listener, with some knowledge and insights to really think critically about the future of AI.
Yes, and how crucial data security is in shaping that future.
Absolutely.
So keep digging into this topic.
Yeah, read the paper.
Stay informed about the latest research.
Keep learning.
And be part of the conversation about how we build a more secure and trustworthy AI ecosystem.
It's a journey we're all on together.
All right, until next time, keep learning, stay curious, and dive deep.